Alrighty, welcome everybody to lecture number 22. Today we are covering Rust numero trace, number 3. And today we're going to be talking about this thing called, the slice type. We're going to be talking about how to do structs in Rust. And in fact, your homework on Rust over this next week will have a lot to do with kind of interacting with structs. We'll do some review, and then we'll talk about matches, which are like switch statements. And we'll talk about vectors and kind of the similarities between vectors and strings. Why are you yikesing me, Daniel? Oh yeah, don't fight. All right, so let's first just kind of have this idea of what a string is, right? So if we create a string, we have these things in memories of the different letters, right? And what all a slice is just a slice of this, right? A subsection of it, a portion of this larger string. And well, let's look at that in maybe some more detail now. So or more technically, first we'll introduce the idea of slices. Slices allow us to reference a contiguous sequence of elements in a collection. And so in this case, we have this contiguous sequence, the LL and the O in hello, and we only really maybe care about that part, right? Slices don't have ownership. It's really just talking about a part of something that is owned, right? A part of that larger string. And a great example of using a slice is to, access the first word in the string, the last how many characters in a string, things like that. And so one thing that I want to introduce is the reason why we use these slices is because it's actually pretty slow to create these new strings. If you remember from your last lecture, Rust 2, we talked about how you create these things on the heap. And then when we're accessing these slices, it's much faster than having to allocate memory every time. And so this is preferable to that in terms of speed. I'm turning my mic down a little bit because it seems like it was peaking. If it's too quiet, just let me know. Okay, so once again, that string slice is going to be a reference to a part of that string. And so, what's actually going on here? Well, first, we have this reference, just like we talked about in the last lecture. And then we have this string, name, just the name of the variable. In this case, it's reverse me. And then we have this little extra part here, this slice. And, maybe you remember kind of this similar syntax in Python, but nonetheless, we'll introduce it one more time. So a string is a list of characters. If we have reverse me, we can assign an index to each one of these. And so when we say, 0.7 in these square brackets here, what we're saying is I want everything from the 0th character up to and not including the 7th character. And so we can maybe visualize this a little bit. And so reverse me is pointing to kind of this location. And when we want word 1, we'll also, we'll say, okay, start here and go for, 6 characters, or essentially go for, you want a total of 7 characters. You want to go until the 7th character, however you want to phrase that. And then similarly for word 2, we'll start at the 8th character and we'll go to, but not including the 10th character, or the 10th index, I should say. The 10th index obviously doesn't exist, but that's fine because we're not including it anyway, and so we just get M and E. So, what is this going to print? Well, we can actually test it out and run it. Hopefully, as expected, it prints reverse me. And so what's going on here? Well, again, this first string is getting reverse, not including this space, which is the 7th index. And then the word 2 is getting me, just me. And then we're printing reverse and then me. Okay, so hopefully that makes sense, using these slices. And let's maybe talk about these a little bit more interestingly and maybe a little bit more generally as well. So internally, what's really going on with these slices? Well, these slices are storing two things. Maybe, as we looked here, they're storing where they begin and they're storing how far they go. Right? And in fact, we can even explore these. And so we can take this same example and we can print the location of the word as well as the length of the word. And when we print it, we see, this huge long value here, which is the physical address in memory. And then we print how long this thing is, right? And so what we know is, for word 1, if you go to this location in memory, what you find is REVRSE, kind of 1 byte at a time. Maybe interestingly, we also know that word 2 is going to be this value plus 8, right? Because it starts, 8 bytes later. So there's a quick distinction that I want to make between this string class that we looked at here and maybe these slices, these string slices that we're looking at here. And basically the two most important details that I want to split is kind of this difference between being on the heap and being on the stack. And because we're on the heap, we have this added thing called capacity. So, we have these two pointers. Pointers, once again, as we saw here, are, where this data actually is in your memory. And so, when we're on the heap, we also have to have this capacity. And if we think back to the heap, this is because stuff on the heap could change size. We don't know how big it is, and it could change size. And specifically, maybe if this string became longer, we would need to change the size because we need to not overwrite another piece of data in the heap. Alternatively, on the stack, right, these things are fixed. It's never going to be more or less than 2 characters. It's just going to be ME for its entire existence until it gets deleted. Okay, so let's talk a little bit more about this dot dot notation that we use to do slicing. And so let's say we have some string that we'll just call s. The first thing you can do is just go from 0 to some index in that string. Again, this index is non-inclusive, so if you say 0 to 1, it's the same as just getting the first character. If you say 0 to 2, you get the first and the second character. So if you want to go from 0 to some index, you don't actually have to write the 0. It's kind of inferred, so you can just do dot dot and then whatever index you want. Similarly, if you want to go from some index to the end, you can say some index dot dot and then nothing afterwards. That the last index is inferred as well. It can figure it out on its own. So, maybe a little bit interestingly, maybe not interestingly, hopefully not too surprising, if you want the entire string, you can just say s dot dot. Of course, this is basically functionally similar to just writing s, but sometimes has some small differences in terms of like safety of writing things. And hopefully maybe this looks familiar. We did the exact same thing in Python with the colon, saying, I want this index, stuff like that or slicing arrays in Python. Is this more or less like Java's substring, or is there an actual difference? So there's a little bit of a technical difference on how these strings are actually stored internally. So it's not totally the same. With Java's substring, it actually like kind of creates a new string item on the heap, I believe, while this just kind of pulls it out onto the stack. So basically, the only important difference is that it's actually significantly faster, I would say, than Java's substring. To use this array slicing, but in terms of how you're going to be using it, yeah, it's the same. Maybe it's less characters, so maybe that's a little bit better, right? But functionally, the way you actually use it's the same. So one kind of final thing with these string slices is the actual type of data that we use when we slice a string is a reference to a string. We call it at string. And this is important just to know what you're actually working with and maybe to draw the distinction between this. This is not kind of a proper capital S string, right? This is not on the heap. It's a reference to this primitive data type called a string. And then, also, if you just have a string literal, that's actually a string slice internally. And so if you just say, let literal equal a literal, this is a reference to a string just like this data type, rather than, the alternative being this capital S string, we'll call it. And you might ask yourself, this is basically just adding confusion. Why do we do this? Well, this is kind of a necessary step in order to have this, huge ease of life implementation that is ownership, right? Additionally, to make sure that we can still access strings quickly and access substrings quickly, right? As I kind of mentioned, it's a pretty fast way of doing substrings. And so, as you may be able to imagine, this isn't actually only limited to strings. This is, works with any type of array. And so, am I stuttering? I'm not stuttering on my end, but it's possible. Uh, if someone else is stuttering, let me know. In either case, we can use these slices on things that are not only strings, and so we can use them on actual arrays. And so, we have 196, 196. If we say 1 dot dot 3, what's that going to do? Well, we start at the first index, which is a 9, and we go to, but not including, the third index, which is a 1, and so we get 9 and 6. And, this is what this comment says, and so that must be the truth, right? Okay, so we've talked a little bit about slices, we've talked a little bit about strings, and even how these slices can apply to arrays. Again, these things are just kind of useful tools for getting substrings. You'll use slicing a pretty good amount in your upcoming homework, and so I encourage you to maybe at least understand kind of what's going on here, and especially one bug that many students run into a lot is not necessarily remembering that this is non-inclusive. So this is not including the third index, right? This does just give 96 and not 961. Okay, so let's talk about structs. This is another big part that you'll be working with in your homework. A struct, as you mentioned in, I think Rust 2, maybe it was Rust 1, unlike Python, our arrays cannot have multiple data types. Our arrays have a single data type. And so if we do want to maybe store multiple data types together in a meaningful way and access them and work with them, we use structs. And of course, structs are a thing in many languages, and Rust isn't, I'd say, functionally different than any specific language. And so hopefully this might be a little bit familiar, or at least, in the worst case, it will prepare you for a lot of stuff that you'll be seeing in 128, 225, things like that. So a struct is a custom data type that allows you to group variables or group values together that don't necessarily have to be the same data type, right? In this situation, we can have a struct that represents information about a UIUC student, right? And you have a name, you have a UIN, you have maybe a value saying if you're a 196 student or not, and you have a GPA. Now, of course, your name is a string, your UIN is a number. If you're a 196 student or not is a Boolean value, right? It's true or false. And then your GPA is a float. I should say the UIN is an int, but yeah. So how do you create a struct? Hopefully, once again, not too surprisingly, you use the struct keyword to create a struct, and just like any other variable, you'll give your struct a name. Inside of the struct, when you're instantiating it, we do want to make sure that we're giving it actual values inside, right? We talked about how these different things are things that we want to keep track of for our UIUC student. And so what you do for this is you say the variable name and then colon and then the type that that variable is. This might look, something similar to a dictionary. It's basically the exact same format. So let's look at maybe a more concrete example. We can see struct UIUC student. We have our name, which is a string. We have our UIN, which is a unsigned 64-bit integer. We have, if they are in 196, which is a Boolean value, true or false. And then we have their GPA, which is a float. So how do we actually declare a struct? Well, we use that same pattern that we saw just before. And so, once we've declared that this, UIUC struct is a thing that exists and it's a thing that our compiler and our program should know about, we can create structs from that using this format here. And so we have, let student1 equal our new UIUC student, and we pass in information for each of those. And so for our name, we want to make a string, and we'll call them E1 nightly sticks. This was not my joke. This was Rohan's, but I had to keep it in because it sounds like 196, right? Get it? Anyway, we also give them a UIN, right, which is a number. We give them if they're in 196 or not, which is true in this case. And then, of course, all 196 students have a 4.0 GPA because you are the best and the brightest. And so, we set that to 4. One thing, I do just want to kind of keep in mind, these are all totally separate values, yet we're finding this kind of nice way of storing them all together in one spot. One thing to keep in mind is these key value pairs don't have to be in the same order, right? We could have done GPA in 196 UIN name, and even though it's in maybe this order in the original struct declaration, it's fine. True. Um, one thing that does have to be the same is kind of this name here, and so name does have to line up with name, UIN with the UIN in 196 to in 196, right? And as hopefully not too surprisingly, these data types have to line up, right? If you try to set the name, which is expecting a string for, to an integer or a Boolean value, well, maybe it'll try to force you to, maybe it'll force the conversion, but it's definitely not something that you want to do. So, and this is kind of a key part of these structs is when it comes to actually accessing values inside of these structs and getting the value back out of it, we use dot notation. And so in this example here, we'll actually just open up the code example. We'll kind of break this down piece by piece. And so first, obviously we have our function. In our function, we'll define this struct type for UIUC student. Once again, name UIN in 196 GPA. And then we'll actually, create an example of this. We'll say let student1 equal, 196. Their UIN in 196 is true, and then their GPA is a 4.0. And then when we actually want to get that, we say student1, being the name of this struct, dot name. We're going over Rust 3. We're talking about structs. And so we say .name accessing this name attribute of the struct. And in fact, when we run this, we can see, there's some warnings for stuff being unused, but in the end, we do get the name at the end, right? Okay, awesome. So let's continue. So we can see we do get that name at the end. There are some warnings for stuff being unused, but don't worry about that. Just because it's uh, it's because it's unused, right? A lot of the parameters. In either case, we can access multiple values. In fact, we can even edit these values, right? And so we have our student here that we want to be mutable. Once again, if you want, to have things be mutable, as we mentioned, things are by default immutable, and so you do still have to have this mutable keyword here, right? So if we want this to be mutable, mark it as mutable, and then we can change the GPA here. Right? And so we have the GPA 3.5. Yeah, the student maybe just took Gen Chem, and so their GPA drops to a 3.3, and we can print out their name and their GPA, and we can see it does successfully change. Now, one thing to keep in mind is it's really quite impossible to have a mix of mutable and immutable things inside of a struct. There are ways of doing it. The ways of doing it kind of break the reason why any of this exists, right? So basically, just keep in mind if you're going to have a struct, either everything can change in it or none of it can change. And the whole reason why we have this mutability is so that multiple threads can be run, kind of working with the same stuff. So yeah, in our situation, just always have the entire struct as mutable or immutable. Individual values, we're not going to make individually mutable because it's A, very hard to do so, and B, a bad idea. And because this is this because this is this new data type essentially that we've created, we can return it from a function, for example. And so we can build a function here where we'll say function, I want to create a new student. And then my headphones will turn off. Function, I want to create a new student. We'll pass in a name, which is a string, a UIN, which is a unsigned 64-bit int, and we'll return this UIUC student type. And once again, we'll actually create and return this here if we remember the syntax. If you don't put a semicolon and it's just this last thing, by default Rust knows that this is what's going to get returned, right? And so what we'll do is we'll return a new UIUC student struct with the name as name, the UIN is UIN, and then for defaults we'll just say they're not in 196 and their GPA is a 4.0. So once again, this here is what the function is returning, and we kind of the important part is we can set this equal to our struct type. We have some parameters that are going into here, and then for the other stuff, we don't need to pass it all forward because we're just going to say by default they're this. And we can demo this as well. So let's kind of first read this from the top to the bottom. We'll say in our function, first we will create a new student, and then we will print their name and their GPA. The new student, we're hoping to have a name function student and a UIN of 196.196.19. We create this thing, we actually say, hey, there's this thing called a UIUC student. It's a struct. This is the data that's inside of it. And then we actually create a function that's going to return this. And in this function, we set the name equal to be the name that we passed in. We set the UIN equal to the UIN that we passed in. And, that'll get set to func student, which we then print the stuff of. So let's run this. Let's see what happens. Once again, we get the warnings of unused stuff, and we can say function student's GPA is 4. And so, this was correct. We can see function student correctly got passed in. The 4.0 GPA was correctly kind of default set, and so, life is good. Everything is happy. Now, we can actually even make our life a little bit easier. You might notice some redundancy. We're saying name, name, UIN, UIN. We can be lazy. Rust has this fancy name for something called field initialization shorthand, and basically this just means when the variables and the parameters have the same name, you only have to put it once, right? And so we can go back to this same example, and we can actually just change this to say name and UIN. We'll run it. And we can see it still works the exact same. So, maybe some characters are saved there. There's a lot of little quality of life things like this that it has. But, maybe we can even take this a step further, believe it or not. So, let's say this is maybe a very, very large struct with many, many, we'll say, attributes to it, and you actually don't want to type them all. And maybe the attributes are a lot of characters too. And, maybe you only want to change a couple. We can do this thing called struct update syntax. Okay, and so, the big idea here is we want to make a new struct, and basically we're going to copy stuff from a different struct. And we can use struct update syntax to do this. So, we want to make our new struct, and we'll say, in 196 and GPA are, maybe they're the same, right? Instead of, and basically instead of reinitializing each one, we could do it this way and get the value and pass it in and get the value and pass it in, but that's way more characters than just typing false or 4.0, and maybe it's more complex. But in either case, we can generalize this even more, and we can just say dot dot student one. Right? And so what does this actually mean? What this is saying is all of the things that I have not explicitly told you what they are, copy them from student one. Right? And because student 1 is also a UIUC student, it's going to have all of the same attributes as student 2 needs to have, right? And so what it's going to do is everything that isn't name, everything that isn't UIN, which in our case is only GPA and in 196, it's going to copy directly from student 1. And so, maybe it's a little bit confusing that we're using the dot dot here again, but, basically the dot dot is saying copy everything else from student 1. Okay, so next, we'll talk about a little bit of a special case of structs that are still very useful called tuple structs. Tuple structs essentially look like tuples, if we remember Python tuples being basically immutable lists. Similar to structs, they provide some meaning by what you call them. Maybe UIUC student, represents that it's a UIUC student, and maybe a tuple struct represents some coordinates, and you want to call it coordinates, right? The only major difference is that the specific fields we don't give names to, right? So if you had coordinates, you could give it, X, Y, Z, or maybe if you have more than 3 coordinates, you could start getting crazy like A, B, C, D, E, F, G. In this kind of tuple struct example, we actually don't give it a name. We just say the data type. And this is pretty valuable because it kind of groups a couple different types of variables together and makes it so that they're kind of grouped together. They have a new name that represents information about them. It's just kind of a cleaner way of doing it, I would say. It's a way to write kind of cleaner code. So, we can create two tuple structs here. We'll say struct test scores 3 ints, struct lecture reviews 3 ints, and then we can actually instantiate two of them. And so for test scores, you get 10, 20, 30. For lecture reviews, you'll get 5, 5, and 5. And so, kind of the important thing to keep in mind here is these don't have a name. If we'll see in a second how to access them, but normally when you access them, you'd say dot name. They have no name. So what are we going to do? Instead of using the curly brackets, we use the parentheses. And one thing to keep in mind is even though internally these two structs are the exact same, being 3 ints in a row, they are not the same data type. And your compiler and your program knows they're not the same data type. And so if you have some function, for example, that expects test scores and it gets lecture reviews, it's going to yell at you because you passed it the wrong data type, right? Okay. I've never heard of parentheses being referred to as round. Did I say round brackets? Whoops, I meant parentheses. Maybe I meant curly brackets. I don't know. Round brackets is strange. Um, so which of these is the name for Rust? Oh, I need to actually make the poll, don't I? So we're going to do some review here. Poll V8 4. Okay, so if you go to pollbot, we have our first poll question. When we're doing package managing in Rust, or even what is the pollbot doing? Oh, this is strange. Yeah, this is strange. Hmm. I got a bug for Tim. Oh, cool. Okay. Um. Hmm. Okay, try now. Okay, it looks like it's working. That's an interesting bug. Okay, if you answered either one, you'll be good. So don't worry too much about that. So which of these is the name for Rust package manager? Additionally, we explore that this package manager is maybe a little bit more than that. It's also the way we compile and run these programs. And so hopefully you do know the name. I'll give it a couple more seconds. Okay, closing the poll in 3, 2, 1. Great. Yeah. So everyone knew it was cargo. Great work there. Of course, pip is the one for Python, Maven, Java, npm is a JavaScript thing. So you will say, does this code work? I accidentally clicked and spoiled it, but it's okay because this one's not a quiz. So we have let change me equal 5. The variable has the value blank. Change me equals 20. The variable has the value blank. Right? Is this going to work? Hopefully, maybe you remember this from Rust 1. Of course, I spoiled it, so I won't wait for a response. No, by default, these variables are immutable. So if we actually do want this to work, what do we need to change? There's two ways. Exactly, Afnan, no, because it's not mutable. Great work. Yeah, so this will give you an error. It'll say, hey, you're setting an immutable variable. So what would we? Yep, let mute is one way. Can anyone tell me the second way? Exactly, redefining the variable, doing shadowing, right? And so maybe in this example we can explore that. And so we have let var equals 10, we'll increment it by 1, multiply it by 2, divide it by 4. Is this going to work? Yeah, absolutely. Yeah. So no trick questions here. This will work. We're using shadowing and overwriting it. Once again, maybe I'll remind you, shadowing is basically redefining a new variable, uh, and just calling it the same thing. I had my water bottle behind my computer, and so my computer fans heated up my water bottle, and now I have warm water, which is so uncomfortable. Anyway, can my array have multiple types? If I have an array, can I put a string in it and an int and a char and stuff like that? Listen, I'm not like Matt, all right? I give you nice, straightforward answers. Nothing is ever a trick question. Ever. Right, so can my array have multiple types? Believe it or not, this one is still not a trick question, and so no, your array cannot have multiple types. Nope. Yep, didn't do the poll bot. Didn't do the poll bot. Yep. Here you go. There you go. All right, let's pretend like that didn't happen. So there's the poll bot. I'm sure that this is a real tough one. Real thinker. To anyone who joined in the past 15 seconds, it's yeah, flip it. It's what? What do you mean, lecture 13? There's like that doesn't count. That's still production quality. Okay, I'm gonna close the poll since I don't think anyone else is answering. So we'll close in 3, 2, 1. Wow. Wait. Okay. To the one person who put 1, um, it's 2. Your array cannot have multiple types. In Python, it could. Obviously, we kind of did that a lot in Python, but in Rust, you are restricted to only having it be a single type. As a quick reminder, let's talk a little bit about the stack of the heap. And, one thing that I want to mention about the stack of the heap is you will talk about these in depth. If you take, 128 or 225, you'll talk about, really the intricacies of the stack and the heap. But in our case, what we're going to, generalize it as is we use the stack when we want to store a data of a known and a fixed size. So we know how big it is. We know it's not going to change. We put that on the stack. For data on the heap, we know it's maybe, we really don't know how big it is. We know how much memory we want to allocate for now, but eventually it could grow, right? We have maybe some string, and, we know it's at least 20 characters for now, and maybe one day it'll become more, and if it does become more, that's okay, right? We can reallocate and make a greater capacity for it. Let's talk a little bit about ownership. Of course, each value in Rust has a variable that owns it. Each value can only have one owner. And when the owner goes out of scope, we essentially lose that value. And so, why do we actually do this? Why do we have ownership? I want to talk maybe a little generally here for a second. It's because Rust really does focus on this whole thing of concurrency and parallelism and having maybe multiple threads do similar tasks, right? Personally, I think that I come from kind of more of the compy background, and I can tell you, that's going to be a huge, huge focus over the next many years is parallelism and concurrency, right? Us compies have done as much as we can making the CPUs faster. We're kind of hitting the limit now. And so a huge amount of speed up is going to start coming from, parallelism in code and making things parallel. Oh, hey, Matt. How you doing? So basically, what I'm saying is, CS majors got to step it up and write better code, like Matt. Listen, Matt, if you want your computer to catch on fire, we can just put more transistors in there. But, Anyway, so we did a little bit of review here. Somewhere we I think lost a slide. So maybe this is lecture 13, but when you actually want to access variables inside of these tuple structs, you can say .0 for the first one, .1 for the second one, dot two for the third, etc., etc. Oh, actually, we didn't lose the slide. I remember where it is. Moore's law is okay. All right, Matt. So let's talk about match keyword. So match is really similar to the switch statements. It's just a way. Rust has taken a little bit of a different approach with it, and so you can argue that they look different or are a little bit more powerful. So we'll take a peek at that. So, obviously in Java, you have your syntax, you have switch on your expression, case X, case Y, and your default. When we actually want to look at maybe a physical example or implementation of it, we can say, we want to switch on this variable called day. If it's 1, it's a Monday, 2, Tuesday, 3, Wednesday, etc., etc. Do you guys start your days with Monday or Sunday? I always say Sunday is one, but maybe that's frowned upon. Yeah. I wonder why that is. Tu- Tuesday? Okay. So we can do it very similarly in Rust. We have a number, we want to match on the number, and let's kind of break down what's going on here. And so first, instead of saying case X, case Y, we use these arrow brackets. And so everything to the left of the arrow bracket is what you're matching for. Everything to the right is what essentially happens after that, right? And so we say if number is 1, then println 1. If number is 2 or 3 or 5 or 7 or 11, then we want to print that it's a prime. If 2 is between 3 and, essentially between 3 and 19 inclusive, this equals says, also including 19, then we want to print that it's a teen. And if it's anything else, we'll just print that it's not special. There's no other special numbers in the entire world. So, we can match a single case. Yeah. Um, it's fine. We can hard code all the primes. There's not an infinite amount, right? Anyway, maybe I just made all the math majors mad. Um, we can match multiple cases, we can match a range of cases, and we can even match kind of our else, our default case, where we just say, everything else kind of fits into this. Or if you didn't match one of these before, go into here. And we can actually start to get, I guess, really quite powerful with this. And so we can use this thing called destructuring to, and we actually, this is a similar thing in Python as well that I think we talked about very briefly. But we can do destructuring to break apart tuples or structs into their different pieces. We'll look at tuples right now because they're a little bit simpler. If you do want to learn about how to destructure, structs, you can look into that. So in this situation, we'll have, just a triple, maybe it's XYZ coordinates, and we can say match triple. I want 0, Y, and Z. So what's happening here? I want to match where the first character is 0 or the first number is 0, and then I want to pass Y and Z, no matter what they are, into this part here. And so then you can say first is 0, Y is this thing, Z is this thing. Again, these are being passed into this function, and so you do have access to these. Now, alternatively, if you just do a dot dot saying, whatever else, we can say, the first one is a 1. So if the first character is a 1, we go here. Y and Z, doesn't really matter what they are still, but I also don't really care about passing them in. And so we wouldn't have access to them here. If we tried to say, first is 1, Y is this, and Z is this, it would say, we don't have access to Y and Z. That's not in this scope. We're not passing it in. And then, as always, we can use the underscore just to say, basically, ignore this, who really cares? And so let's try this out. We'll run it again, let triple 0, 0, -2, 3. We see that it works correctly. And if we switch this to 1, -2, 3, we can see that it hits the second case. Now, if we switch it to 5, -2, 3, we can see it hits the third case. It doesn't really matter. Now, maybe interestingly is you can switch it to 0, -2, 3, 54. And so what's going to happen here, right? Well, this is only expecting 3 values and it's getting, or sorry, yeah, it's expecting 3 values and it's getting 4, and so it's going to yell at you there. But if we did this with 1, because we're essentially saying, I don't really care about the rest. Oh, did I miss a? Oh, haha. What did I typo? Oh, okay. So, all right, it's making me work for it. Anyway, we can see that, it hits this second case. In the first case, it was trying to compare something with 3 elements to 4, and that was giving us an error. Trust the compiler? I should trust the compiler, but I like to pretend that I'm smarter. I can't talk. Smarter than the compiler. So we have this really powerful thing for tuple deconstruction. This is just like super handy and super cool, and so we thought it would be nice to teach the best and the brightest about it, right? And believe it or not, this is actually also a similar thing in Python. It's not quite as powerful, but you have this what's it called? Decomposition, I think it's called in Python. I can't remember the Pythonic term for it, but it basically does the same thing. Smarter. Eustis. Yeah. And we can even have these things called guards. And so even our match statements, instead of only passing variables in, we can have, kind of more complex if statements about them. And so, well, what are we saying here? Well, we're saying, I want to return x if x is, divisible by 5 and x is divisible by 3. Right? And you could even get crazier with this. You could say I want to return x times 2 if x is divisible by 5 and 3, and then maybe you do something with that over here. Or, who knows, right? The idea is that you can use these guards to have really complex match statements, and it, even with the addition of this destructuring, you can do kind of really crazy stuff inside of match statements. Okay, so we'll talk about vectors, and that'll basically be the end. One thing that I want you to keep in mind when we're talking about vectors is basically the similarity with strings. So vectors are a data tool. It allows you to hold basically, a similar thing to array, except this is basically going to be on the heap, and it allows us to store, still, only values of the same type, but it's kind of arbitrary type. It can be even, structs, things like this, right? We refer to the vector saying vec t, where t stands for type. And so, let's say we want to have a vector of integers with, 32 bits. We can say, let v vec in 32 equal vec new. Okay, so what's going on here? We're creating a variable called v that is a vector of 32-bit integers, and we're actually instantiating it, right? We're creating it on the heap. Again, this starts as an empty list, and so nothing crazy there. But you actually can make your life a little bit easier if we remember that println vec or println macro. We can use a different macro called vec. We can say vec exclamation point and just automatically fill it with data, right? We don't actually have to do this maybe verbose implementation of it, right? We can just say this. So we can say let v equals vec 196. So, one of the kind of key properties of vectors is if you set it to mute, it is mutable, and we can kind of actively change it, and we don't really have to worry about the size getting too large or too small, right? If we have, something on the stack, we would have to worry about that. And so, we can push to this vector, we can push 1, 3, 4, 5, and we'll look at the example here. We can see that this runs without problem. And so, we're kind of able to successfully push things to this vector without, it yelling at us and saying this isn't mutable. And so, one thing that I want to introduce you to now is this idea of sum and none. And so, we have this idea of, we have our vector of 196, and we want to get a reference to the second value, right? And so in this situation, we say, let second equal v of 1, right? Second index or first index, second value, and we'll print that out. But what if we don't necessarily know if that exists or not? What we can do is use this sum or none kind of syntax. These option types is what we call them, optional values. And so we'll try to get the second value. On the situation that we match the second value, we'll say, sum third. If there is some value in third, then we'll print it out. If there's no value in third, if this thing didn't exist, if it returned none, then we can handle that just like this. Right? And then, so in the second case, ideally this grabs the 6. We'll say the third element is 6. But in this case here, when we're getting 100, in this situation, there is no 100th index. There's no 101st item. And so we're expecting there to be none. Yeah, match is very powerful. And so we'll run this and we'll say, okay, well, this is working correctly. The second element is a 9. This is working correctly. It's saying the third element is a 6. And so it's kind of grabbing this correctly. And the reason it's grabbing this correctly is because, this is returning some value, right? This isn't returning none. This does exist. But then when we try to do it on an index that doesn't exist, right, there's none there. There's nothing there. And so this will return the none type. And we can handle that in our match statement. And, we'll print that there's no 100th element. And so we can see that that is fully functional here. So great work to us. So, again, I just want to introduce you. You can use this sum and none type to basically handle the cases where it may or may not contain a value. And there's kind of a lot of things like this in Rust that really make your life very easy. And then finally, we'll talk about iterating over vector. Similar to Python, you can just say for val in v. Again, we'll throw the vector or the reference in there because we want to iterate over the values. And that's pretty much it. I mean, it's not too crazy. You always have the option to do kind of the classic for I in range, ABC, v of I equals whatever, right? And set it or read from it that way. But, it's not necessary. We can do the more Pythonic way of doing it like this, which is, kind of handy, I guess. I definitely like doing it like this a lot of the time. Okay, well, that's pretty much it for this lecture. We talked about a good bit of stuff. We talked about match statements. We talked about vectors. We talked about, we did some review. And then really we talked about strings and structs. This kind of slicing and structs is pretty important, I think. And you'll use it a lot on your homework. And so hopefully you'll get comfortable with it that way. Of course, if you do need help with the homework, just come to office hours, stuff like that. I do believe we have a social hours after this lecture, and so come on by if you want to hang out. I'll be there. Matt will probably be there. But if there's no questions, I think that we'll end the lecture here. Thanks everyone for coming to Rust 3, and I think you'll see Matt on Thursday for something. Lecture number 23. Which I can't remember the topic of off the top of my head. Okay, see ya.